So before I jump into the main part of the talk, I would like to make some clarifications which were based on some of the discussions we had the other day. So I would like to highlight basis independence. So at a given mass dimension, whichever basis we choose, the number of operators would be the same. They would not be different. So they will always be the same, because the number of operators forms a vector space in a specific mass dimension, and it's invariant under an invertible change of basis. So whether we are taking the Warsaw basis or the Silch basis or any other basis, the number of operators would always be the same. So this is a bit small, I'm sure, but here you can see, like if you look into the slides later on, this summarizes the category of operators in the Warsaw basis, and this one does in the Silch basis. So here psi basically represents a fermionic field, phi a scalar field, and d the covariant derivative. So these are all the possible combinations that exist in Warsaw basis, and these are the forms of operators written in the Silch basis, and this is in the intersection, which these forms of operators exist in both the bases. And from going from one basis to the other, so we had exactly seen it, how it works for the toy example, but here, which ones?
Not on the overlap.
So there are 1, 2, 3, 4, 5 operators, which are 5 classes of operators. These are not the operators themselves, these are the classes of operators. So it's written in a cryptic way. So phi to the power 6 would mean, say, h to the power 6. So psi to the power 4, for example, are 4 Fermi operators. They could include all kinds of fermions. They could include the doublets, the singlets, and so on.
So I should not be trying to match the numbers.
So these are not the exact number of operators, these are the classes of operators. So if you remember here, these are the classes of operators, so that I am referring to here. And these are in the Silch, and they are related. So this is a bit small. So this Banerjee is not me, so it's linked, the paper is linked. So if you actually see, these operators are related from one basis to the other through these equations of motion. So the classical equations of motions that we discussed the other day. Other than that, we were also discussing how, so there are papers which actually count the number of operators at a given mass dimension. So this method is called the Hilbert series method of the SMEFT counting. It has been done by Hitoshi Murayama, Tom Melia, and others. So this is the function that is used. So I won't be discussing this entire process, but I have given a lot of information in the backup slides, and you are free to come and discuss with me, but it would take a long time to discuss this whole thing. So this is the Hilbert series generating function, where these t, they basically are the weights, the so-called weights, which actually could be the mass dimension of an operator, the flavor of an operator, and so on. And the an basically counts the number of independent gauge invariant operators of that weight. So finally, with these methods, this platistic exponential and Molian Weil integrals, which I have discussed in the backup, in the extra slides, you will be able to see how for every mass dimension we will be able to get the exact number of operators which will be invariant under the symmetry in hand. So this Molian Weil integral would include the group structure, so the gauge structure while doing the integral, and it would include all the invariants and would remove all such redundancies. So that's the beauty of this method. And by doing this calculation in the standard model effective field theory, for instance, in the Warsaw basis for dimension 6, we get 2499 independent parameters with 3 generations of fermions. Yes.
This Hilbert series method,
Yeah.
does it take care of the integration by parts and the equation of motion?
Exactly. So
that
it
takes
care of the equations of motions. So that actually comes into this Molian Weil integrals.
Okay.
So if you click on this link, you will directly go to that those things.
So equation of motion comes from the tree level.
Equations of motion comes from the tree level at dimension 4 only. So that's another point that I was coming to in the next slide. Yeah.
And then when you do integration by part, it
Yeah.
tells you that the theory is invariant under the change in the boundary conditions.
Absolutely. Absolutely.
So that gives another constraint.
That gives another constraint.
How are the Warsaw this?
So Warsaw and the Silge bases are defined here in this sense. You will see that most of the Warsaw basis operators are written in terms of the fermionic fields, whereas most of the Silge basis operators, barring a few, are written in terms of the gauge fields. So that is the difference in which these operators, these bases are written. So they are for different experimental purposes, that's about it. But they are like analogous of one another.
Just one more clarification, is this Hilbert series method, does it take into account very crucially the representation of the Lorentz group?
It does take into account the representation of the Lorentz group, yeah. So the other day Shanmoy asked this question whether the partition function should remain invariant. So the thing is that the partition function per se, so if we change the field phi to say some f of phi prime, so phi prime goes to some f of phi, so when we write down this d phi, it would come with an additional Jacobian. So that's why this partition function exactly might not look the same. So this action which has the Lagrangian density in it, which is a function of the field phi, that would now become a function of the field, function of phi prime, and this d phi would come with a j of phi. So even though that's the case, but if we have local and invertible field definitions, the physical observables which are basically coming from the S matrix would remain unchanged, even though the partition function in itself can look different. So it's the same quantity, but it can look different. The other thing, the other day there were questions, so I thought about it a bit, like why should equations of motions, like whether, or I think you asked this question, whether or not we should be including the operators with different redundancies at the level before doing the equations of motions. So as it turns out, the classical equations of motions, which are derived by the Euler-Lagrange equations, they are obtained from the leading renormalizable Lagrangian. So the EFT Lagrangian is not a renormalizable quantity. So we deal with the leading renormalizable Lagrangian and we derive the Euler-Lagrange equations, and we leave out any subleading terms which are in the expansion parameter of 1 over lambda, and we get these equations of motion, and then we use these leading order equations of motions to cancel the redundancies. So these are some of the clarifications that I wanted to say. Now
that analysis will be valid only up to that power of 1 over lambda.
So
there can be higher
the
order
equations of
sections.
motions will only involve the dimension 4, in this case dimension 4 Lagrangian, and it would only involve the standard model like fields. So it would in this case the equations of motion, if I am dealing with SMEFT, will only involve standard model. So I'll derive the equations of motions from standard
What is the
model.
logic behind it?
So the reason is that we want to derive the equations of motion from a renormalizable theory.
Why?
So other like if we do not do that, so it's again a choice. So that's why like there's an error of the order of O lambda to the power minus 1 or O lambda to the power minus 2, but these are not fixed quantities. So every time we choose a basis, so it would be different. So the difference, the order lambda to the power minus 1 or order lambda to the power minus 2, when we introduce some redundant stuff, it would not be the same. The equations of motions would keep on changing. So we fix the equation of motion with the renormalizable theory that we deal with, and then we use those results in the dimension 5, dimension 6 and so on case.
So if we had used the right equations of motion, it would have corrected higher order terms.
Yes.
But since we are allowing all possible higher order terms,
exactly,
using that,
exactly,
because you have to fix those coefficients anyway.
There are infinite number of terms in that Lagrangian. Yes, absolutely, yeah. So by irrelevant, that we also discussed the other day, when this canonical dimension D is greater than 0. Is there a question? No. Oh. Okay. So the other day we discussed how to go from an effective field theory to some operators, like, or a theory, a UV theory to some operators from the top down approach, or from the bottom up approach we do down operators. But finally when we talk to experimentalists, or we talk among each other, we won't be talking in terms of the operators, but we will be talking in terms of the observables, which are the physical quantities which we will be measuring. So in order to study the phenomenological effects with the inclusion of these higher dimensional operators, it will be easy for us to work with the mass eigenstates rather than working with the full invariant formulation of SU3C, SU2L and U1Y. So these higher dimensional operators that we will have, these will broadly lead to two deviations with respect to the standard model. One is it would lead to modified couplings, which would give corrections to the strength of the standard model like interactions, and the second is it would give rise to new vertices which were before not present in standard model. So in standard model we have certain kinds of vertices which exist, but by the inclusion of these higher dimensional operators we will see that we will have either or both modified couplings as well as different vertices which did not exist in the lower mass dimension Lagrangian. Okay, so let's consider this operator OHE. So we had defined this operator when we discussed the Warsaw basis. So OHE is an operator for the right-handed electrons and the Higgs field and the covariant derivative. So this is how the dimension 6 operator is defined. So now after symmetry breaking, if we insert the Higgs wave, so this would lead to a coupling of the Z boson to the right-handed electron. So if we open up this, so I would encourage you to do it as a homework exercise. Open up this operator, plug in the covariant derivatives, the Higgs fields and everything else, and then what we get is that from here we will get an extra term. So for example, Z mu E sigma mu EC bar. So this would be a function of the Wilson coefficient of this operator and suppressed by the scale lambda squared. So this is the term that we will be getting. In standard model, the Z boson coupling to fermions, we know this is a familiar expression. So we will have both. So this comprises both the left-handed couplings as well as the right-handed couplings. In order to obtain the right-handed coupling, we set this T3 to 0 and the QF will be equal to -1. So this is my right-handed coupling of the Z boson with the right-handed electrons. So now I see that this GZE was my original coupling. Now it has encountered a shift because of this operator, and this is the shift quantity. Now this is something that would be like over and over we will encounter, is that from a single operator in standard model effective field theory, we will have different kinds of couplings. So just like this OHE, when you expand it, it gives rise to a Z coupling to a pair of right-handed electrons. It would also give rise to a coupling like a Higgs, a Z and two right-handed electrons. Note here that the dimension of this term is 5. So this is 1 and 3 by 2 and 3 by 2. So this is a 5-dimensional term. So that's why this term did not exist in standard model. So this is a higher dimensional term that comes. So the same operator gives rise to different kinds of terms. So that is why it was seen that in the LEP experiment before the LHC at CERN, there was another experiment, LEP, Large Electron Positron Collider. There one could measure the decays of the Z boson and the W boson very, very precisely. But the Higgs boson was not discovered back then. So if the standard model EFT is a correct form of the theory, through such correlations like the ZEE is now measured or constrained, this operator, the same operator would have been able to tell us that a Higgs-like particle existed even before the discovery of the Higgs boson. So this is the beauty of the effective field theory, the standard model effective field theory formalism, which correlates various different couplings, and we can actually see that. So this new vertex, which involves this Higgs, Z and these two right-handed electrons, so this affects the amplitudes of the Higgs boson. So the Higgs decays to, for example, to 4 leptons via 2 Z bosons, one on shell and one off shell. So this kind of a vertex actually leads to the modification in the Higgs decay width as well as the distributions of the Higgs to 4 leptons. So this is studied at the LHC, and from the LHC studies, such operators can be very strongly constrained. So we will have many different measurements. So for example, the measurement of the Z boson's width from the LEP collider, the Higgs differential distributions from the LHC, the Higgs width from the LHC, and we'll have different kinds of measurements and we'll be able to constrain this operator pretty well. However, mind you that here I am just talking about a single operator. In reality, we will not have one operator, but there will be many operators in question. So we will be able to ultimately constrain a linear combination of these operators' coefficients. That's about it. So we will not be able to specifically constrain one operator unless we have the number of data points equals or is more than the number of observables that we have or the number of operators that we have.
Let's say for the E plus E minus collider, so within standard model I can actually produce the Higgs and Z boson.
Yes.
So what is the like when you argue that in the E plus E minus collider even you don't know the Higgs, you can give the bound, but still I can do the computation of standard model and try to find the Higgs there.
I am not sure about the question. So if I try to understand the question, we are
so E plus E minus going to let's say Z boson,
Higgs,
and then Z going to Z and Higgs.
Yes.
So you see Higgs and Z in the final state.
Yes.
So from there I can actually see like whether Higgs is. So there should be enough energy to produce the Z and Higgs.
Yes, but then what's the question?
Question is that like I mean even if we don't know the EFT, but still from the standard model we can predict that Higgs is there in the E plus E minus collider.
Yeah, now we have predicted it. Before observing it, what I am saying is that before observing the Higgs from the LEP collider, LEP's energy was not enough to discover the Higgs boson. But from the SMEFT framework, by reanalyzing the data, we are now sure that we could have made statements about the Higgs boson even before the discovery of Higgs. That's what I said. Now you know that Higgs exists.
No, in this operator, what will be the final state for the LEP collider? From this operator.
So this is
What is the process where we can prove this
so
operator?
this will be the diagram. So this is a 4-point interaction, right? So it will be like this. So this is
So that means you are producing Z and Higgs in the final state.
yes.
But that was not possible in the E plus E minus collider.
That was not possible in the LEP collider.
Yeah, LEP
Yes,
collider.
exactly.
I'm not getting actually. I'm not understanding how from this operator you are going to keep bound in the LEP collider.
I did not talk about LEP collider at all here. So here I talked about the LHC, for instance. So here I talked about LHC. So when the Higgs is produced by any process, so now we have this. So Z going to E plus E minus, and we had Z star going to E plus E minus, but instead of that what we'll have now is something like this at the LHC.
LHC is fine, but when you make comment that we can predict in the LEP collider what are the operator you have written, so what are the processes actually we can prove there? Given that you cannot
processes. It's
given that you cannot produce the X in the final state.
I can produce it at like beyond, not at LEP for sure, but in future colliders I can. What I meant was this one. So E plus E minus Z or gamma star E plus E minus, that is what I said I can probe at LEP. ZEE, because remember here the same operator also couples ZEE and not just HZEE. So this is where I talked about LEP collider. So this is what was constrained at LEP. Is this clear?
What was the statement about EFT being able to talk about?
So EFT through this operator I am able to constrain. If say for example this was my only operator O of HE, then I'll be able to constrain this operator through LEP measurements. Now because this operator also brings about this coupling, this HZEE, even before discovering the Higgs boson, I would be able to put a constraint on this coupling which comes in front of the Higgs boson. That's it. It's as simple.
I could be wrong, but this, not only this, but in the EFT approach, you would be predicting many more.
Many more, a lot
things.
more. Yeah.
And also, this can be seen from bottom-up approach.
This is till now we are talking about bottom-up approach only. I am not talking
Okay.
about top-down approach here.
But you said UFT,
I said EFT.
but not without integrating out.
No, without integrating out.
Okay.
Yeah.
I get confused about that.
Okay. Shall I proceed? Okay. So here we will be able to can the slide be switched off, please? Yes, please. Juhi has a question.
So as you mentioned, the Z going to EE coupling is bounded from LEP already.
Yes.
So that should also constrain CHE.
Yes.
Right.
Exactly. That constrains CHE. Yeah.
So that is now consistent with the measurement of this HZZ star coupling. I mean, I just want to
HZZ
understand
star,
how
yes,
does that constrain the Higgs
Yes, so
coupling.
these are different machines, right? When you have LEP machine and an LHC machine, you will get different constraints. With more energy, you will get stronger constraints. So you have to see whether at LHC you are getting a constraint which is at least stronger than LEP. That's basically the point. And the answer is yes. You get stronger constraint than that. But apart from that, at LEP, mostly E plus E minus like operators were being constrained because we were not dealing with a lot of quarks. At LHC, we have also quark induced operators, we have gluon induced operators. So when we get a constraint, we will be getting a constraint on the linear combination of it. So it's very hard to disentangle just the portion of CHE or OHE, for instance.
And to have this linear combination, again, one has to come to a same scale. And I mean, so the LEP is at 200 GeV or something, and the LHC is at a different scale.
To combine, to say that like we are agreeing with two different scales, like measurements done at two different scales, we need to do RGEs in order to say that, okay, my measurements are now, we are comparing apples to apples. Otherwise, we are comparing apples to oranges.
Okay, thanks.
Okay. So now the effective Lagrangian for the Higgs boson, for instance. So this is the effective Lagrangian. So I am still not talking about the operator still. So here I have written it in terms of the kinetic term, the mass term, the trilinear term. So this one factor basically is the standard model term, and this is being introduced because of some effective operator. And then we have a different kind of trilinear term which comes with two derivatives. So the delta 1 term modifies the standard model like triple Higgs coupling, and the delta 2 term is a new two derivative interaction. So now I had discussed redefinition of fields before. If we redefine the fields, we will be able to get rid of some kinds of couplings which are probably looking bad or are hard to deal with in our calculations. So if we redefine the Higgs field as H plus delta 2 V by 2 lambda squared of H squared, what we get is, we get a very, like we get this term, like similar looking term. So instead of that, we get delta 1 plus delta 2, and we get higher order terms. EFT post breaking, exactly. So yeah, yeah, that part, like when I discussed that, you probably just missed it. So now I am talking about EFT post breaking, because when we talk about observables, it's much easier to deal with the mass eigenstates, the post breaking scenario, than in the fully gauge invariant scenario.
I see. But such a term couldn't have arisen from a pre-breaking EFT, right? The last term, for example.
This term,
The H del mu H del mu H.
it could have come from a loop term, for instance.
I see.
At tree level, no. So this is what we get, and as we discussed before, if there's a good description, a good redefinition, by equivalence theorem, this redefinition does not change any of the physical observables. So what do we want? We basically want to constrain these operators. Like how precisely can we measure, or rather constrain these operators by the end of the run of the Large Hadron Collider, or if there might be any future colliders and so on. So basically these couplings, the SU2L coupling, the U1Y coupling and the vacuum expectation values, these are determined from these three very precisely measured observables. So we have the Fermi constant, we have the electromagnetic fine structure constant, and we have the Z boson mass. So these are very precisely measured quantities, and the higher dimensional operators can shift these relations. So for instance, if we take an operator h dagger d mu h squared, so this is one of the operators in the Warsaw basis that we saw the other day. After the electroweak symmetry breaking, we will be again similar to what we did for the OHE, we will be able to write down the Z mu, the Z mass contribution. So we will be able to write down the GL squared plus GY squared V squared by 8. So we will be able to get an additional contribution to the Z mass. Similarly, we will also get a shift in the W boson mass. But we know that these are experimentally measured quantities. So what we will need is, we will just need to redefine the standard model parameters using these corrections. That's what we need. So the Z boson mass has been measured very precisely, so 91.1876 GeV with a very small error bar. So, and as the Z mass is used to extract these couplings GL, GY and V, the contribution from this operator OHD complicates this determination, because previously we were trying to just determine 3 parameters from this mass. Now we are trying to probe 4 parameters. So if we assume that OHD is the only higher dimensional operator, mind you, this is just a toy example, this is not reality, because we have lot more observables, lot more operators, so this is just for illustration's sake. The constraint on this Wilson coefficient is going to be minus 1.2 plus minus 0.9 by 10 TeV squared. So I have left a detailed example in the backup slide, so if you guys are interested later on, we can go through this, or if I can finish my main slides, which I am not sure I'll be able to, we can go through this explicit example. So this indicates that the electroweak precision measurements can actually probe this weakly coupled new physics. So when I say weakly coupled, it's coupling of the order of 1. So if the coupling is of the order of 1, then my scale of new physics would be of the order of 10 TeV. However, if I am in the regime of a strongly coupled scenario, so if it becomes of the order of 4 pi, then the new physics scale would become something close to 100 TeV. So this ratio is something that we would be constraining, but then, as I discussed before, our assumption of whether the theory is a weakly coupled one or a strongly coupled one would determine what kind of new physics scale that I am dealing with. So now I wanted to discuss, so we discussed tree level matching with this toy UV theory. I just wanted to give you a glimpse of how one loop matching works. So I'll be discussing the case of 2-point functions where we'll have these 1 PIs, but for 4-point functions, because we discussed at tree level pi pi to pi pi scattering. So the 4-point function would take me a long time, so I would leave that as an exercise, as a curiosity, but I'll discuss the 2-point function. So the 1 PIs, the 1 particle irreducible parts, so for the EFT we will be able to write it as p squared minus m squared. So remember, this is the mass which is going in the loop, and for the UV it would be p squared minus ml squared. So remember, these were the original Lagrangian, so this was my UV Lagrangian with mass ml, and this was my EFT Lagrangian with mass of m. So now if I induce dimensional regularization, so from the EFT one loop correction would read delta pi of EFT would be in terms of this function, this Wilson coefficient C4 m squared by 32 pi squared, then we'll have this 1 over epsilon bar, where because we are doing this calculation in dimension d minus epsilon. So 1 over epsilon bar, where epsilon bar is defined as 1 over epsilon plus the Euler constant plus log of 4 pi, plus we'll have a log of mu squared by m squared, which this mu term basically comes when we are doing the dimensional regularization plus 1. So here we'll be able to do this calculation either in the unboxed basis or the box basis. So we discussed these two bases quite a few times in our last lectures. Sorry? Where
No, I'm just asking whether you're in D minus epsilon or D
d
minus
minus epsilon,
not to epsilon.
not to epsilon.
Just one question about the previous things. So the electroweak precision measurements that you're talking about. I mean, this is probably a very naive question. How do the dimension 5 or dimension 6 operators break custodial SU2?
So yeah, there is one operator which is custodial SU2 violating.
At dimension
At
6?
dimension 6, there is no custodial dimension violating, custodial symmetry violating operator at dimension 5. At dimension 5, there is only the Weinberg operator that we talked about, and that operator is very, very strongly constrained from the row parameter measurement.
I see. So the dimension 6, how much custodial violation, custodial SU2 violation do we see, and is that consistent with this dimension 6 operator?
So the dimensions, whether it's consistent with the dimension 6 operator is not, I think it's not the right way to put it. We have the custodial violation, we have rho 1 plus like 0.99 plus minus, I think the uncertainty is of the order of 0.1% or something, if I recall it correctly. So that translates to the constraint on this custodial symmetry violating operator. But the thing is that if that operator in some observable comes as a linear combination with other operator coefficients, then we are not directly able to probe it, but as it happens, there's only one single custodial symmetry violating operator in standard model EFT at dimension 6. Right. So this is basically in the unboxed basis. If we do the calculation seriously, we can discuss this later on, but I wanted to give you like some more material rather than sticking with one single calculation. So in the unboxed basis, we'll see that we'll have no wave function renormalization, whereas in the box basis, we'll see that when we calculate the Green's function will include off-shell contributions to the momentum p squared. So in the unboxed basis where we are doing this calculation, when we calculate the m squared, we'll see that there is no off-shell contribution, no such momentum dependence, whereas in the box basis we'll see some non-trivial wave function renormalization when compared to the unboxed basis. So we use the ms bar prescription, which is very easy because it not only gets rid of the 1 over epsilon, but it also gets rid of some of these constants like the Euler constant and the 4 pi. So here what we do is we simply subtract the 1 over epsilon bar pole to render the amplitudes finite. So that's the ms bar prescription. The renormalization scale, the mu, is basically introduced by dimensional regularization, and the Lagrangian mass parameters will become mu dependent, because the Lagrangian mass parameter needs to become mu dependent such that the final physical observables that we calculate are not mu dependent. So the physical mass for this EFT calculation in the unboxed basis, it's defined as the pole of the pi of p squared, and we get it as m squared minus c by 4. So we can actually see that from the propagator inversion, if we write a triangle propagator inverse of p squared, we will be able to get for very small values of if we do a Taylor expansion, we will be able to see that it comes out to m squared minus c by c4, m squared by 32 pi squared, and this log of mu squared by m squared plus 1. So this is the physical mass squared, but you see here still this mu is hanging around. So to keep the physical observables mu independent, this mass must then satisfy this dm squared d log mu is equal to c4 m squared by 16 pi squared. So I'll be discussing the renormalization group evolution in a bit, but all of these are important. So finally what we have in mind is that the calculations that we finally do, the observables that we finally calculate, they should be independent of this mu parameter.
Inverse of the propagator, so it will not
It would be zeros of, did I write pole? Oh sorry, yeah, this should be the zeros of pi p squared. So this is how it would look like. So we will be able to write it like this. So So just for everyone's benefit, this is what we get. So we will be basically getting so this is equal 0, and that's what we, is anyone monitoring it? Anyway. Okay, so from here we basically get m phi squared so to do it explicitly, yeah. So the UV so till now we talked about the EFT. Now if we come to the UV, so remember here for the EFT we'll only be using this diagram. For the UV we'll be using all these 4 diagrams. So there will be 4 diagrams. The first one where we'll have a light particle in the loop. For the second one there will be a heavy particle in the loop. The third one there will be a light particle in the loop, and in the fourth one there will be a mix of a heavy and a light particle in the loop. Yes.
So about this physical observable comment, like we know that this scale depends on the scale.
Yes.
So once you talk about the bare
Yes.
parameters, they don't depend upon the scale,
Yes.
but the physical they depend upon the
Yes.
scale. So in the next slide, when you make the comment,
So I'm saying the dimensional
Go to the next.
regularization mu, that's what I'm saying.
yeah, go to the next slide.
Yes.
So to keep the physical observable mu independent, so why actually physical
For
observable?
example, if you are calculating a cross section at a certain energy, that should not depend on this mu. That's what I'm
They
saying.
depend on the mu. Like if you are not doing the all order correction, then they will depend.
Exactly. So if we are doing an all order correction in the EFT, it should not be depending on the mu. So we should be, so that the renormalization group, what it would be doing, it would be summing over the logarithms. If essentially when we do a full calculation, we'll be summing over all the logarithms to all orders, and then the mu dependence should go away.
Yeah, but here you are truncating that series.
Here I am truncating, but ultimately what I'll be showing in the RG, that it will be summed over all. So it will be a resummation of the logarithms
So
basically.
when you set this condition, so that means in the truncated computations you say setting these conditions,
Yes.
which is not true actually.
What is not true? I'm not getting your point actually.
You are truncating the series,
Yeah.
so then we will expect that it will be dependent upon the mu. But at the same time, you are demanding that that should be mu
You
independent.
still see there is a mu here, right? So the statement that I made here, that the Lagrangian mass parameters become so the physical observables become mu independent is when I add all the orders.
So in this equation, you take dm physical square by d mu log equal to 0,
Yes.
and from there you are setting the condition, the last equation.
You can keep on adding all these terms. So I'm expanding about this value. So you can keep on adding all the terms. So
The last equation, how do you get it? From the previous equation, setting the physical mass derivative 0.
exactly.
No, not this in the slide.
Yes, this
The
one.
last equation you are getting from the previous equation by setting m physical mass to be independent of the mu by taking
Yes.
the first derivative 0.
The thing is that for other higher derivative terms, they will all be suppressed. So instead of an equality, it should be almost equal to. So there will be higher order terms which will all be suppressed, and we'll finally need to resum all these terms.
The definition of m phys, what m phys square, what is the definition? That is the propagator is fine, p square minus m
Yes.
square minus
Yes.
plus this, and that has a precise prescription of how to calculate pi.
Yes.
Now once you calculate, then what is the-
Now I do p squared is equal to m phi squared. I do the calculation at p squared is equal to m phi squared,
Yeah.
and that's what I do here. And I put this equal to 0.
Can I just ask a clarification question? So this m phi squared is scheme dependent, right?
Yes. Can I continue? So in the UV, this m phi squared can be again written down in terms of ml squared instead of m squared, and all of these parameters C4. So for example, this lambda 0 minus 3 lambda 1 squared minus 4 lambda 1 squared ml squared by m squared if you remember from the toy example, we had matched at the level of the tree, at tree level, and we had found C4 is equal to lambda 0 minus 3 lambda squared minus 4 lambda squared ml by m squared. So, and there are other terms. There is one term which has a log, and depending on the value of mu, we'll have whether this term blows up or whether this term is really small. So, we'll finally find out that when the scale mu is of the order of m, which is my high energy scale, then this term would actually fall off, and that's a good choice. So, because the operators are created at the scale m, when we have this mu of the order of m, these terms, this term would fall off. I am coming to it in the next slide. So, the UV theory will have a different mass parameter. So, ml is different, and these couplings would be different, and these would lead to extra contributions compared to the EFT, because in the EFT we did not have these other diagrams. Here we have all these other diagrams, so we have to sum over the amplitude from this and this. So now what we do is that we match these two. We match this m phi squared from the EFT to the m phi squared from the UV, and what we see is, so we have a cancellation of this term. So this term can be replaced by C4. So this and this term actually goes away. So we are left with minus 1 over 32 log of mu squared by m squared times this, and we also have m squared lambda 2 squared plus blah blah blah. This is the entire term. So if we set this mu of the order of m, this large logarithm actually falls off, because if it doesn't fall off, then there will be a difficulty while doing perturbative expansion. But if we take this mu to be of the order of m, this term would become very small and we can get rid of it. So in the dimensional regularization, it regularizes the loop integrals by working in dimension 4 minus epsilon. I just kept this slide for everyone's benefit. The MS bar scheme, basically it simplifies the renormalization by subtracting all the universal 1 over epsilon bar term. When we do an EFT versus UV matching, the EFT loop corrections are matched to the UV theory to define scale dependent mass parameters consistently, coming to Bishwajit's points. So here are we see scale dependent mass parameters, and now coming to naturalness, the matching condition now reveals that how these UV parameters determine the EFT mass, with the natural scale being m squared of the order of m squared by 16 pi squared. So how is this 16 pi squared coming? So this term falls off when we choose mu going to m. Then this term, basically m squared by 32 pi squared, or we can actually see that the mass is of the order of m squared by 16 pi squared. So that is basically the natural scale. So if we are doing a careful matching with mu of the order of m, this would actually avoid large logs and would allow us to do perturbative calculations properly. One has to do these carefully. So I wanted to flash these results, but if you want to sit down and do these calculations over this week, I'll be very happy to discuss with all of you. Now coming to RG equations in the EFT, now we discuss in the unboxed spaces. So in order to ensure that the physical observables, that is the physical mass, the S matrix elements, that these remain independent of the renormalization scale mu, the EFT parameters should also run with mu. So we had the mass running with mu, we should also have the EFT parameters running with mu. So in the unboxed basis, the one loop RG equations are the one that we already wrote down, dm squared dd log mu is equal to m squared c4 by 16 pi squared. So this we get from the 2-point function, and this calculation when we do it from the 4-point function, which I did not include, I can include it in the backup slides, my handwritten sketch. So dc4 dln mu, we get 1 over 16 pi squared, a 3c4 squared plus m squared by capital M squared c6. So we see that there are two kinds of terms here. One is m to the power 0, which is this term and this term. So this reproduces the standard phi-4 theory, while this additional m to the power minus 2 term, this shows the effect of the dimension 6 operator. So what we see is that when we do loop calculations, at one loop, these Wilson coefficients of the higher dimensional operators, which is this D6 operator also affect the running of lower dimensional ones, but not the other way around. So,
Shankhu,
yes.
So I think this here these equations, the running equations are being calculated from a different way. I mean, not what Vishwajit was referring to. He's
Okay.
referring to the standard process where you demand that dd log mu of a bare quantity must vanish.
Exactly.
It's not exactly
Here
that.
we are not demanding
It is matching condition.
It's a matching condition. We are not requiring the bare quantity to vanish here.
Sorry, I'm a bit confused. Let's not talk about ill-defined objects like bare quantities. If that's the case, you just write down Kalan semantics, everything finite.
Yes.
You just say
No,
Kalan
it's not-
semantic.
I don't
whatever
think that's
works.
ill-defined.
Bare quantities are ill-defined. Come
No,
on.
no, no. That is how you calculate RG.
That's not true. You write down Kalan semantics and you say everything should be consistent with Kalan semantics and you compute.
No. Calculation comes from something.
No, Kalan semantics is dimensional analysis. Anyway, where was
What's the
I?
question?
That's what I was going to ask. So in the EFT, do you write down Kalan semantics and compute these things, or how? I mean, how do you? I mean, the question initially that I was going to ask is that the Kalan semantics seem like they don't close. Like, is that true? Because if you just write down the Kalan semantics, say two of the Kalan semantics,
Yeah.
it seems like you need a 6-point Kalan semantic to
Yeah.
eventually. Then you'd probably need an 8-point Kalan semantic and so on.
Yes.
So is that
So here we are doing a 4-point 4-point calculation in this. So we get this relation by doing a 4-point calculation, which I have not included here. So we basically get phi phi to phi phi, and we have the loop. We have multiple loops. That's where we get this relation from. So what I wanted to, does it answer your question?
But
Yeah.
no, the other part of the question was how did you compute these?
Oh, so I basically what I did was I calculated the pi of phi phi. So for example, so for the 4 loop calculation, we have to cut the loops and we have to do the calculations. So that would take me some time. So if we want, we can do it offline.
I just meant the rough procedure. I mean, like, what did you start with? Kind of okay.
So we basically started with all the possible 4-point diagrams. So we basically have this would include the light phi's as well as the heavy phi's. There will be many kind of diagrams similar to what I did before. I calculated the physical quantity, this m phys again, and then so there I also calculated the corrections to the C's, the C4 and the C6. Those corrections are also coming from these kinds of diagrams. So that's what I explicitly calculated, and that's how I'm coming to this relation here. So what I wanted to impress upon you is that the Wilson coefficients of higher dimensional operators, they would also affect the running of the lower dimensional ones when there are some explicit mass scales present. So here I wrote down the first RG equation. So if I just integrate this equation, what I get is m squared mu is equal to m squared m mu by m to the power c4 by 16 pi squared. So that's what I get by integrating this RG from the 2-point function. And if I demand that c4 by 16 pi squared times log of mu by m is much less than 1, I can write down, I can expand the m squared of mu as m squared of m 1 plus c4 by 16 pi squared log of mu by m. So this kind of here I have used this relation a to the power epsilon is e to the power epsilon log a, and I have expanded this. And for this expansion parameter, I have required that c4 of log mu by m is much smaller than 16 pi squared. So this modification of the naive scaling is owing to the anomalous dimension. So this is what we call the anomalous dimension c4 by 16 pi squared. So this could become a matrix if we have more than one operator at play. So this is the anomalous dimension. This would be translated to an anomalous dimension matrix. So this is due to the anomalous dimension c4 by 16 pi squared. and the RG evolution basically resums all the large logarithms that we encountered from the UV theory into the EFT parameters. So they would be resumming them and putting them into the EFT parameters, which would ensure the consistency between the EFT and the full theory, even when this C4 log of mu by m becomes sizable. So we'll see that it's not just the size of the coupling which matters, but whether or not there are large logarithms at play or not. So if there are large logarithms at play, we'll always violate perturbativity. If we can resum the large logarithms away, then it's a good calculation. It's not a sick calculation. Okay. So now I wanted to discuss, just completely shifting gears now, I wanted to discuss how do we constrain these EFT operators from data.
Is it, before you move on, is it
Yeah.
possible to say in few words what the matching condition is conceptually?
So the matching condition is basically what it is. So we take a UV theory of our choice and we take the EFT. So the EFT at a given order is specified. So it has a lower dimensional part of the Lagrangian plus the higher dimensional part of the Lagrangian. The difference between the two Lagrangians is that here, if you observe, so this part is exactly the same, the del mu phi squared and the m squared parts are the same. However, when we come to higher dimensional operators like for example, if we take a full theory, we integrate out the heavy physics like heavy field like the H, then we do not have any remnant of the H here. What we have is some phi to the power 4, some phi to the power 6 and so on. So now what we do is we compute some process. It could be a scattering process, it could be a decay process, whatever we want to, a physical process we want to calculate. We calculate it both in the EFT and the UV and we match the coefficients of the various terms. So here, for example, we had done this.
So this is top down.
Yeah, like matching is always in the top down scenario. Like we are matching EFT with a UV model.
So if you had started with LEFT, that one, and just did renormalization.
If I started, so I will not be able to do renormalization of this theory until and unless I cut it off at a specific mass dimension. Because this goes on, this would go on, this would be like in a real theory, this would be 1 by m to the power 4, 1 by m to the power 6 and so on.
Yeah, they will mass suppressed.
Yeah,
You
they'll be
could
mass
still-
suppressed.
You could still do counter term renormalization of that Lagrangian.
But there will be infinite number of terms.
But they are mass suppressed. There is
There-
always-
yeah, so we'll be able to
this
do.
is not
we'll be-
this UV is not unique. You
yeah,
could have
it's
started
not
out.
a unique UV.
Yeah, you could have started out with a different UV and
Yes.
generated other terms.
Absolutely.
So that cannot be a
renormalization of EFT is usually talked about at a specific mass dimension. So we talk about EFT. EFT is a non-renormalizable description.
Non-renormalizable doesn't mean that you cannot do counter term renormalization of that theory.
We can do it, but order by order. So we can fix order at dimension 5.
Yeah, you are doing the same thing here. You are not sure about the higher order terms because you are not sure about the UV theory.
I don't know the UV theory as well as I do not know how many more terms will be there, like how many operators will be there. So that's what I don't know. So
that's an experimental error. That
exactly. So the renormalization, if we do, so there'll be many more counter terms, many more divergences to absorb in there. So if we fix a dimension, if we say fix dimension 6, then we'll know the exact renormalization that we want to do. It would be an exact calculation at dimension 6. So because I know the exact number of operators, 2499. That's the maximum number of operators that I have at dimension 6 in the standard model EFT.
Yes.
We have to compute a 2499 cross 2499 dimension matrix. That's what we need to do.
Yes.
And people have done that. Okay. So at dimension 8.
I'm saying that if you had started, whatever you said so far that we cannot it is non-renormalizable and so on. I don't think those are really problematic things.
It's not problematic.
Problematic things, okay? I'm saying that if you started out with this low energy effective theory with higher order terms which are non-renormalizable.
Yeah.
And then had renormalized that
Yeah.
and had calculated running,
Yeah.
that result would be different.
Absolutely. It would be different. It would be different. Like what
I think Vishwajit's question is
what
in that
UV
context.
No.
Here something else is being imposed.
So what model I choose, like if I choose a different UV theory, that would, so if I choose UV theory number 1, I will get M1 set of operators. If I choose UV theory number 2, I will get an M2 set of operators. Now this M1 set and M2 set may not be exactly the same. They could be different sets. From both two UV theories,
Yeah,
I
I'm
may
saying
not
that-
get exactly the same set of
I'm
operators.
saying whatever procedure you are following from starting from UV
Yes.
theory coming down to here, I'm saying that if you started from here
Yeah.
and did counter term renormalization
Yeah.
and calculated running,
Yeah.
I think you would get a different answer.
So from bottom up you mean?
Yes.
Yes,
I'm
we'll
saying
get a
bottom.
different answer. Yeah. Because in the bottom up, there's another difference. In the in contrast to the top down, in top down, all these operators are not independent from each other. The Wilson coefficients are actually functions of the UV theory.
Okay.
But from a bottom up approach, they are all independent parameters.
Okay, so then if the running is different for the different couplings, these
Yes.
couplings can be viewed as coming from UV,
Yes.
top-down approach,
Yeah.
or
Or
in the
bottom
context
up.
of bottom-up. They're the
Bottom-up.
same couplings.
Exactly.
Now, Sanmay said that his PhD work was to verify running of a coupling. So in principle, probably it is not practically possible, at least now, but in principle, looking at the running of those couplings, one could figure out whether it's following bottom-up or top-down. Is it
We
a
would
right
need
statement?
enough. So because there is
we need it's
in
maybe
principle
practical.
yes, in principle yes, but we need like huge amount of data
That
compared
is
to what
fine.
we have
but
now.
in principle,
In principle,
is there a,
yes.
is there a
In principle, yes, we'll
signature
be-
that can distinguish these two
Yes,
scenarios?
in principle we will be able to distinguish these scenarios, and that is actually what we can see from the matching graphs that I am about to show you in the next few slides.
So in this slide you mentioned, the previous one. So here you also mentioned that C4 runs and that can also mix with the C6 operator. So in the next slide, does this C4 also contain that effect of C6 operator as well, or
Yes,
that is
so
suppressed?
exactly. So like this, so whenever we, so this is the RG, this when we apply the RG running of C4, we see that it gets contributions from the C6. So if we use an R, wherever we use an RG, like as C4 which has been RG run, it should include the effect of C6 at a different energy scale.
Okay. Okay.
So coming to an explicit example, how we do global analysis. So here we wanted to see these specific sectors. So we have these 23 operators. You can count these later on. So we have operators which contribute to di boson processes. By di boson I mean 2 W bosons being produced, 2 Z bosons being produced, a W and a Z and a photon being produced, and so on. Electroweak precision observables, like we'll have the S parameter, we'll have the T parameter, the Peskin-Takeuchi parameters, then we'll have the di-Higgs, we'll have the single Higgs. So these are all the 108 data points that were taken from experiments which included electroweak precision observables from LEP as well as WW data from LEP and then Higgs data in various channels from the Large Hadron Collider. Both of these include the Higgs data, so the ATLAS experiment, the CMS experiment. Then we have some other kind of data like some di boson production, some Z plus some jets production, some di boson production again, and some di Higgs production as well. So all of these data actually will be there to constrain the set of 23 operators. So this is right now what we have. These data are a comprehensive list of data which would constrain these 23 operators or these different classes of operators. So what we do is that we do a chi-squared analysis or a log likelihood analysis which are equivalent, and what we find is that we are able to constrain all of these. I'm not going through all of these like the exact results, these 23 operators to such certain precision. So we see that we are able to constrain these values c over lambda squared. So we are not saying anything specific about c or lambda, and these constraints on these 23 operators are done from a bottom up approach. They are not done from a top down approach. So we are doing it from a bottom up approach, and these are the constraints that are derived through a global analysis. So this is called a global fit. So now if we try to match a top down analysis with a bottom up analysis. So we take a classic example of a 2 Higgs doublet model, where in addition to the standard model Higgs like doublet, we have another doublet H2, which is basically coming with, it's a color singlet, it's a spin iso doublet, and it has a hypercharge of -12, and this is the Lagrangian. So we have the standard model Lagrangian, which is d equals 4, and then we have all of these other terms, which includes the kinetic term of the second Higgs, the interactions between the second Higgs and the standard model like Higgs, and so on. So this is the Lagrangian that describes the 2 Higgs doublet model. So I'll zoom on some of these operators. So what we do is that then we, at one loop, we integrate out this heavy field H2. We integrate out this heavy field H2 and we get certain number of operators. So I'll zoom in on them. So these are the three classes of operators that we get. The one in the black, the red and the blue. So one in the black is basically, these are functions of the 2 Higgs doublet model parameters. So we see that these are functions of these eta H2, YH, Y, SMD, and so these are all functions of the 2 Higgs doublet model parameters. The red ones are also functions of that, but they do not. So remember, I started with a set of observables which we deal with these 23 operators. These operators in red actually do not affect this current set of observables that I am dealing with, and the blue ones are actually not functions of the 2 Higgs doublet model, barring this energy cutoff scale. So this energy cutoff scale will always be there in all of these operators because they will be suppressed by this new physics scale. So these are the three classes of operators that we get: the black ones, the red ones, and the blue ones. And we only deal with these black ones because these are the ones which are functions of the 2 Higgs doublet model operators and also constrained by the set of observables. This is the set of observables that I talked about, the set of observables.
After integrating out the.
After integrating out, yeah.
So that's a top down.
That's a top down.
What is the meaning of top down plus bottom up? What do you mean by that?
So top down plus bottom up means that, so I'll be coming to these slides. So here we have basically plotted these operator coefficients CH versus some CHB. So there will be many such combinations. So there is one, this big region, which is the bottom up approach, from the bottom up approach. So remember here I got these global fits. In the first lecture I discussed, I showed it on the board that there's a big region which comes from the bottom up approach. So this big region is basically coming from the bottom up approach, and what we have are small regions. It's not visible very well. The small regions inside, I forgot to include the zoom in graph, would include the top down graph. So on the same parameter space, CH versus CHB, I have included the bottom up results, which is what we derive from this global analysis, and top down result, which is a small subset of this region.
Is this result sensitive to the RG flow that you described?
Exactly. So we included RGE and we included next to we did the calculation at the leading logarithm. So this is how we define. So we already saw that for the toy example, there was a 1 by 16 pi squared, and this gamma was basically a number, and we had the operator coefficient. Now we have many such operators. So what we do is we write it down as the anomalous dimension matrix and we sum it over all possible operators. So this is basically my RG running equation, and by solving it I get, so the operators are created at the scale lambda, which is high up, and then I use them to see the effects at the value of the Z mass.
That's in the top down approach.
That's in the top down approach. So in the same graph I include the bottom up and the top down approach, and I also see that whether or not we choose the RGE the region actually changes. So
There is no RG in the bottom-up approach. There is no RG equation that has been used.
exactly. So only the top-down approach, the region has been used. So this will actually change the region. So if we include the RGs, the region that we get from the top-down approach would become more relaxed, because before it was a function of, so now these operators mix among themselves and the regions become more relaxed. So because of this anomalous dimension matrix, the operators that we started with, so we started with 37 operators here, which were generated at this cutoff scale lambda. Now we use the RG evolution equations, and we will see that not only will the coefficients of these operators be different, they will mix into each other, and it will also create certain new operators. So the RG evolution also creates new operators. So it creates new operator coefficients. So that is what we will see, that for the 2 Higgs doublet model, we started with 37 operators at the scale lambda. When we look at the operators at the scale mz, there are 14 additional operators of these forms which come into existence.
And the region for the bottom-up approach, what is the calculation there?
So for the bottom-up approach, it's not a calculation, it's a numerical analysis. So what we do is we calculate, so for every vertex, so for example, say we are studying Higgs process, Higgs decaying to some say ZZ star going to 4 lepton. So we know that what operator contributes there. So we know the shift in that coupling with respect to the standard model. So that is my theory for now, and we have all these data. Using the theory and the data, we do a global fit using a chi-squared minimization. By doing a chi-squared minimization, I get a range on these operator coefficients from the bottom-up approach, and that's what we plot. So we get, if there were 23 operators, there's a 23-dimensional hyperspace, and we are looking into 2D slices of them.
And if you go to the next slide, this picture, yeah, and in future experiments, if you show that you are outside that restricted space, then you would change your UV theory.
It would change my UV theory. Yeah. Any more questions? So now I just wanted to show very briefly. So I think I started 5 minutes late, right? So I have 5 more minutes. So, oh sorry.
Sorry, I forgot. Yeah, you can go ahead.
Yeah. So till now I talked about the standard model effective field theory, or the SMEFT. Now I wanted to talk about the Higgs effective field theory. So standard model effective field theory may not be the most general description. Like, when might it not be the most general description? When the new physics that we are talking about is not completely decoupled. That when the standard model like physics is still talking to the heavy physics. So if I have a heavy physics, in my assumption for the standard model effective field theory, it was that the mass generation of this heavy physics has nothing to do with the standard model like physics. So they have their own mass generation mechanism in the UV theory. In the Higgs effective field theory, we are not restricting it to that. We are saying that it might be possible that a fraction of the mass of the heavy physics might be there because of the standard model like physics. So what it shows is that, so in HEFT, this Higgs effective field theory, it's basically a superset of the standard model effective field theory, which is a superset of the standard model. So are there any scenarios where only the Higgs effective field theory can describe the low energy effects of BSM and SMEFT cannot? So actually there are. So if we have some 2 Higgs doublet model scenarios where the masses of some of the heavier particles get a fraction of their masses from the standard model mass mechanism, then even if we take these masses very high, like up tending to infinity, we'll still not be able to decouple them. And then we cannot use the SMA EFT parameterization, we'll have to use the HEFT parameterization. So the low energy interactions will now only follow the U1 EM, not the SU3C cross U1. The interactions will not be able to tell us more about the properties of the microscopic theory. So new non-decoupling strong dynamics, so if we have some new non-decoupling strong dynamics,
Even if you send the mass to infinity, it doesn't decouple.
it doesn't decouple because there is some relation, like it still gives mass. Like if I take the scale to infinity, what I'm saying, like if I take the scale to very high values, it still completely doesn't decouple. So if there is some new non-decoupling strong dynamics, it spontaneously breaks the electroweak symmetry and we get a Higgs-like scalar. But in this case, in the Heft-like scenario, the standard model is not recovered when all the BSM masses are taken even to infinity. So in SMEFT, we see that if we have a non-analyticity in the Lagrangian, field redefinitions would get rid of those non-analyticities. However, in HEFT, if there are non-analyticity in the Lagrangians, they cannot just be removed by field redefinitions and they will stick around. So these would arise when new states are integrated or acquire masses from the standard model like electroweak symmetry breaking. So this will violate the decoupling. So in the standard model EFT, what we learnt is that the Higgs is just like the standard model Higgs. So it is an SU2 doublet. However, in this case, the H is not an SU2 doublet, and to have all kind of generality and to give it all freedom, it's considered a gauge singlet. And the Goldstone bosons omega A, they are required to form an SU2L triplet. So in the standard model mechanism, the Goldstone bosons arise from the electroweak symmetry breaking. But here we have completely decoupled the Higgs sector from the Goldstone sector, and the HEFT actually treats these separately, and we can write the Goldstones to be embedded in this unitary matrix U. And the partial Lagrangian of the HEFT can be written down in this part. So we have the Higgs interaction, the Higgs kinetic term. We have this FH, which is described as 1 plus 2a h by v plus b h squared by v squared and so on, times trace of d mu u dagger d mu u, and then we have the potential of the Higgs, which is defined here. I am coming to these terms, and then we have the Yukawa matrix terms. So what I want to impress upon you here is that we see that in standard model or standard model EFT, these A's and B's, they come from the same operators, or in standard model they are exactly related from one to the other. But in the HEFT, they are independent parameters, they are not related to each other. Similarly, we can see that the couplings of the Higgs mass parameters, so for instance, if we have a Higgs mass or Higgs mass, so for example a Higgs mass squared, then what we can have is that we can have a trilinear coupling, we can have a quartic coupling and so on. So in standard model or in standard model EFT, the trilinear and the quartic couplings are related by a factor of Webb. So going from a trilinear coupling to a quartic coupling, we just need to divide by V. However, they are related couplings. So there are many more correlations in the standard model and in the standard model EFT compared to the Higgs EFT. So this is basically.
Could you please go back?
Yeah.
So what is the? I'm just trying to understand the characterization of heft. So you have a U1 gauge field, which is a Maxwell.
Yeah.
And then you have an SU2L gauge field. Do you have the full set of SU2L gauge fields?
I don't have the so the only SU2s that we have here are the fermions. So the fermions are SU2, but the Higgs is not SU2 anymore.
No. I'm asking about the full set of gauge fields. You have a Maxwell field, and then you have the gluon fields and the weak fields. Is that what I have to understand?
We have the gluon fields and the weak fields. I did not write it here. So
okay.
How the gluon fields? I think you asked this question before. I think one of the students asked the question. So to write the weak fields or the gluon fields, we'll have a term like W mu nu times FH, G mu nu times FH, and also W mu times Fh. So all the possible terms that we have in the standard model or in the standard model EFT, those would be there, but instead of the Higgs field, like the H dagger, we will have this Fh there.
Understood. So you're treating the H as a singlet, and then you want a yeah. Why do you want the goldstones to be a triplet?
So the goldstones, so the triplet, I am like, so it basically it follows the analogy of the pion physics. So we basically take what's there in the, when we write the pi plus pi minus pi 0. So it's basically an analogy that's been derived from there. So this is also a chiral perturbation theory like theory. Yeah.
I see. What does the subscript L mean?
Sub,
SU2L?
where
Omega, the goldstones are an SU2L triplet, you say. So what is L?
So this is basically, oh sorry, that's a typo, it's just an SU2 triplet.
Okay, that's fine. And the final question, the B mu, I'm guessing, is the hypercharge U1 field, right?
Yes, yeah.
Why is it coming with a sigma 3? Shouldn't it come with an identity in the SU2? Or am I confusing some different SU2? I mean, if it is the...
This I need to check. Can I check this and get back to you? Yeah, this I need to check why there's a sigma 3 here. Like this I'll let you know later today. So this is my last slide for this set of lectures. So these are the main differences. So the SMEFT is the most general set of local operators which are invariant under this full standard model gauge symmetry. The heft is basically manifest under SU3C cross U1 electromagnetic. Yeah.
Just one more question. So basically, what SMEFT does is takes the standard model and writes the EFT with all of the operators with SU3, SU2, U1.
Absolutely.
And heft is basically forgetting about there having been a broken and whatever not,
Absolutely.
and it's just starting with the Higgs.
It's the SU2 sector, so there is no spontaneous symmetry breaking in this, the same language.
And just starts with color and Maxwell.
It just starts with color and Maxwell, yeah. So the operators here suppressed by powers of new physics scale lambda, and here we will see that they are suppressed by the electroweak breaking scale V. The low energy states will be modeled using the fields which are transformed linearly under all these symmetries, whereas we have in this case, I have written this L constantly. The SU2L U1Y symmetry is non-linearly realized using a multiplet of Goldstone bosons. So this observed Higgs is a component of an electroweak doublet, whereas there is no relation between the Higgs and the Goldstone bosons. This gives us a more restrictive symmetry structure which gives us less number of parameters, and the heft we have less restrictive symmetry structure and a number of more uncorrelated parameters. So I had a lot more examples here, but I think we cannot go. But can I just take a couple of minutes if that's okay, because this is my, is it okay? So I wanted to give like another full example of how we can constrain certain EFT operators in a bottom-up approach. So as I wanted to say that there are all of these different kinds of operators. These at dimension 6 there's 2499 operators, or if you assume flavor universality there are just 59 of these operators. How to constrain these operators? So these operators would be constrained in various ways. So they could be constrained from electroweak precision tests, precision observables, like indirect constraint on these operators like these S parameter, T parameter constraint, or they could be constrained directly from a process like a Higgs being produced with a W boson or a Z boson, a direct process for instance. So in this graph, in this cartoon, what we see is that two protons, it's at the LHC, two protons collide, so this is the beam axis, and it produces a weak boson which could be either a W boson or a Z boson and a Higgs boson. And this weak boson decays to a pair of leptons and the Higgs decays to bottom quarks, and I have taken a thick jet here. So what one can do is that, so I am not going through the details of these analysis. What one can do is that one can calculate the amplitude for this process like PP going to HV using helicity amplitudes, some simple techniques, and one will be able to disentangle this entire process into various angular moments. So we will be able, because there are several angles at play. See here, there is this theta which is the 222 scattering angle, there's a decay angle theta, and there's an angle phi between the two planes. So we are able to break down this entire analysis into these many angular distributions which will be testable at the LHC. So these are the various ways the effective operator can come into existence. So for example, it can modify the quark-quark W or the quark-quark Z coupling. It can modify the W-W Higgs or the Z-Z Higgs coupling, or like we discussed here, an E plus E minus Z Higgs, we can have a QQ bar Z Higgs or a QQ bar QQ prime W Higgs like coupling. So if we are studying these Z Higgs and W Higgs, only these set of operators contribute at the bottom up approach. Only 18 of these operators would contribute in this bottom up approach, of which there are some CP odd operators at play as well. And finally, as I discussed before, we do not talk in terms of the operators finally, we talk in terms of the broken phase. So we will see that what kinds of terms will we have. We will have a term which looks like the standard model, like a Higgs Z mu, but it's modified, the coupling is modified by a factor. Then we will have a completely new Lorentz structure like this Higgs Z mu nu, or Higgs Z mu nu tilde, Cp even and Cp odd. Then we will also have some contact interaction like I discussed here. Oh, it's also here. So we will have modifications in various regimes. So we will either have the coupling modification or we will have the vertex modification as we discussed before. And we can choose whatever basis that we want, and we can talk to the experimentalist in terms of these modifiers. So when an experimental gives her results to me, what I'll be able to do is I'll be able to map these to the operator that I want to. So for example, here I take the Warsaw basis and I'm able to map these deformations to the Warsaw basis. And then I don't have time, so we can use something called the Goldstone boson equivalence theorem. I'm certain everyone knows here. Basically states that at high energies, the Goldstone modes in the standard model, they actually can replicate the longitudinal modes of the weak bosons like the Z and the W. And we can do the calculations, and what we can find is, so this is what I was talking about, the helicity amplitude calculation. We can break down the calculation into transverse part of the amplitude and the longitudinal part of the amplitude, and we can calculate these terms and we can square it and we can derive these angular coefficients, these angular structures that I talked about. And finally what we can do is we can constrain the effective field theory parameter space in terms of certain couplings. As I talked about before, the EFT in the standard model EFT, they are all correlated. Many of these operators are correlated. So many operators would give contribution to the exact same coupling. So in this case, we are talking in terms of something called triple gauge couplings. So triple gauge couplings means where the name is obvious, 3 gauge bosons are coupling together. So this one is 2 W bosons and a Z boson, and in this case 2 W bosons and a photon. And we see that going from the LEP experiment, which was this gray blob, to finally the LHC, we will see that the LHC, even though it's considered a discovery machine from new particles, but it's also a precision machine, and we are able to shrink down the constraint on this parameter space from this to this. So one can see here going from LEP to 14 TeV to, if there is ever 100 TeV, we will be able to constrain these operators much precisely. And I talked about something which grows with energy, and we are also able to constrain some angular deviation. So whenever there is new Lorentz structure like this, new Lorentz structure, we will get new angular deviations different from the standard model, and we will also be able to constrain these very precisely. So I would like to end with this because there are many more topics, and you can have a look at the slides. And if you have any questions during this week, please ask me.
Could you go back to the delta L6, please?
Which one?
Delta L6, the expression you had for the delta L6.
Oh, this one?
Yeah, so the first box is some correction to the Higgs-Ströling vertex from the standard model itself. which is okay.
Yeah.
But then these other black boxed
Yes.
thingies, the CP even and CP odd contributions,
Yeah.
has it been checked? I mean, it's probably true, but has it been checked that these are also BRST invariant?
So these are BRST invariant, but the thing is that, like, when we talk about a specific order in mass dimension, so all these analyses have been done at mass dimension 6. I'm not sure whether these would remain BRST invariant if we add a higher order in mass dimension, but
that's
at
okay,
dimension 6 they are.
Oh, I see. Okay. But okay, I'm just asking for references now. Who has done BRST analysis with like a Higgs theory properly?
So
Can I find this?
from the top of my mind, Adam Falkowski, he has several papers. Let me send you the full references as well. And Adam Falkowski has done it, and Taewong Yu and team, they have done these calculations. So there are quite a few calculations on this subject.
Okay, thank you.
Questions?
Actually, one more question. So while doing practical calculations, do people do it in the unitary gauge, or do people do it in some arcsine with the goldstones, would-be goldstones?
So these are, so at least at this level, so let me just come here. At this level, these analyses have all been done in the unitary gauge.
I see.
But what happens is, when we talk about, let me go back here. Yeah. So when we use this Goldstone boson equivalence theorem, and we replace the ZL, say for example the longitudinal part of the Z boson, by the G0, this G0, and we replace G plus, the W plus minus by the G plus minus, then we are not doing the calculation in the unitary gauge anymore. Because in the unitary gauge, the goldstones don't exist separately, like they are eaten up by the longitudinal mode in order to have these. So the reason these analyses are done in terms of the goldstone modes is because these goldstones are scalars, and a lot of renormalization calculations become easier in scalar field theory compared to when we have scalars plus weak bosons.
One more question. So while writing the heft, what BRST do you respect? Do you respect BRST of just SU3U1, or do you respect BRST of SU3, SU2, U1?
I think we respect only SU3U1.
I see.
But I need to check this once.
Why?
I need to, because the SU2 is not there in this theory at all. So there's no SU2 Higgs. So we do not have any, like the Higgs is not part
Yeah,
of,
it's fine.
the Higgs is not part of an SU2 doublet. So the Higgs just comes as a singlet. So the entire, the entire gauge group is SU3U1.
Right.
Unless I'm missing something. You wanted to say something?
Yeah, so I wanted to ask.
Yeah.
So in HEFT, so what you're assuming is that your gauge fields are of the gauge group SU3 cross U1,
Exactly.
and then your W and Z bosons are massless because
Yep.
it's at the higher scale before,
Yeah.
and then those are a part of the goldstone. So it is a global SU2 symmetry.
It's a global, yeah.
It's a global SU2,
yeah.
and the Higgs is not coupled to that.
The Higgs is not coupled to that.
So it doesn't know anything about that.
No.
Okay, and then if you have this kind of a theory, then since they are goldstone modes, the W and Z, now how do you explain the masses in
So there is, like in the heft theory, there is a mechanism which is described for to get the masses of the gauge bosons. It's not that of the spontaneous symmetry breaking.
Oh, it can happen that you can put in some small mass explicit breaking.
Some
Yeah.
explicit breaking, like we put mv squared.
And the goldstone mode is proportional to square root m, I guess.
I think I had those in the slides as well. No, I don't have it in the slides, but they do have explicit breaking terms, which gives rise to the masses of these bosons.